Okay, so in this course we will be studying quantum field theory. You might ask, you have already learned quantum mechanics in your undergraduate in the first year course, so why do you need to study quantum field theory? The motivation for studying quantum field theory is that suppose you consider a particle. The way you do it in your quantum mechanics is you write down the Schrodinger equation and you solve the Schrodinger equation, you find the solution to this Schrodinger equation, which is the probability amplitude. However, there are processes which, for example, if you consider a decay process, let us assume that you consider the muon decay, mu minus going to E minus plus nu E bar plus nu mu. Then there is no way you can understand a process like this in your non-relativistic quantum mechanics. So, the question that you can ask is, suppose you write down the you want to consider the generalization, relativistic generalization of the Schrodinger's equation. Klein and Godin have already done that. And Dirac also have a relativistic generalization. Klein and Godin generalized it for a scalar field, and Dirac generalized it for a spinor. What you find here is that if you want to interpret the Klein-Godin equation or the Dirac equation, the way you interpret the Schrodinger's equation, then you run into various inconsistencies. So, if you want to interpret it as a particle mechanics, then you run into various inconsistencies. For example, the probability amplitude does not give you positive definite probability and so on. So, you are forced to introduce quantum field theory. In this lecture, we will study quantum field theory in much more detail. What I will do is that I will give you some of the references that will be used in this course, and then we will quickly discuss scalar field theory, classical field theory, and then we will study how to quantize the classical field theory. So, the references are quantum field theory by Schwartz, then quantum field theory by Isaacson and Zuber, an introduction to quantum field theory by Peskin and Schroeder, quantum field theory by Mandel and Shah. Then the quantum theory of fields by Weinberg. Gauge theories in particle physics by Aitchison and Hay. Quantum field theory in a nutshell. By A.G. Then quantum field theory by Ryder, Raymond, and so on. So, almost everything that will be discussed in this course will be borrowed from one or the other of these books. Okay. So, what I will do now is I will briefly review classical field theory, and then I will discuss how to quantize classical field theory and what are the applications of the quantum field theory. So, let us briefly discuss classical field theory. So, the classical field theories that we are going to quantize have various. So, we are going to discuss the classical field theories which are, for example, local, in the sense that the equation of motion contains finite number of derivatives. Equations of motion contains finite number we will also discuss field theories which are relativistic. We will impose Lorentz invariance, and we will also require that the energy have a lower bound. So, we will consider the field theories which have positive definite energy. Let us first discuss the Lagrangian formulation. So, in Lagrangian formulation, what you do, you consider the action which is just integration L dt. The Lagrangian itself, we can write down L as an integration of L over the entire space dqx. where this L here is known as the Lagrangian density. L is the Lagrangian density in general. L is a function of the field, which I will denote as phi, and its derivatives. So, the action can actually be expressed as S equal to integration of L phi del mu phi d4x. The volume element d4x is dt times d cubed x. We will find the equation of motion from this action by using the principle of least action. So, what we will do is that we will set the variation of the action to be 0 with the restriction that the variation of the field delta phi equal to 0 at boundary, at the boundary. This condition will give us the equations of motion. So, let us derive the equations of motion from this condition. So, what is delta S? Delta S is integration d4x delta L, and this is equal to del L over del phi times delta phi plus del L over del mu phi delta of del mu phi. Here I am assuming that the Lagrangian contains only single derivative of the field phi, as well as it is also a function of phi. If there are multiple derivatives, for example, if the Lagrangian contains second derivative of the field phi, then you will have one more term and so on. However, we will not consider that case at this moment. So, let us rewrite the second term here. You can see that the second term can actually be written as del mu of del L over del mu phi delta phi minus del mu of del L over del mu phi delta phi. Here I am assuming that this delta actually commutes with del mu, then you can write this term as a total derivative minus this term. So, Now what I can do is that I can substitute this here, then what I get is delta S is equal to integration d4 x del L over del phi delta phi minus del mu of del L over del mu phi delta phi plus del mu del L over del mu phi delta phi. Let us now focus at the last term. You can see that this will give you a surface integration. However, here we are imposing the boundary condition, the condition that the variation of the field is 0 at the boundary. So, when we use this condition, this term will actually vanish. So, the last term in this equation becomes 0. Therefore, delta S is actually equal to delta S is equal to d4 x times del L over del phi minus del mu of del L over del mu phi times delta phi. However, delta phi is arbitrary, therefore, the integrand must be equal to 0. If delta S is equal to 0, then the integrand must be 0. So, this implies del L over del phi minus del mu of del L over del mu phi is equal to 0. This is our Euler-Lagrangian equation of motion. So, let us now find the Hamiltonian for the system. Again, you do it just the way you find the Hamiltonian in mechanics. In mechanics, what you do, you introduce the conjugate momentum P, which is del L over del Q dot, and then you define the Hamiltonian, which is a functional of Q and P, to be P Q dot minus L. Here you do exactly the same thing. What you do is you introduce the conjugate momentum density, which I will denote as phi of x, and the momentum density is defined to be delta L over del 0 phi, and the Hamiltonian density. So, this is the momentum density. Then the Hamiltonian density H is phi of x, phi dot of x minus L of phi del mu phi. Let us consider a very simple example, the example of a real scalar field, and then let us derive the equation of motion as well as Hamiltonian. So, we will consider the example of a real scalar field and then we will see what the equation of motion is and what is the Hamiltonian and so on. Before that, let me explain the notation that we will be using throughout the course. We will use the space favored metric. So, eta mu nu is 1 minus 1 minus 1 minus 1, or in other words, the invariant length of a vector a mu which is equal to also eta mu nu a nu. This is a 0 square minus a dot a. Throughout the lecture, we will be using this metric, and also we will use natural units. So, we will set h bar equal to c equal to 1 throughout the course. Now, let us consider a real scalar field. The Lagrange intensity for a real scalar field is half phi dot square minus half grade phi square minus half m square phi square. You can rewrite this as half del mu phi minus half m square phi square. All right. So, what is the equation of motion for this system? The equation of motion is given by del L over del phi minus del mu del L over del mu phi is equal to 0. So, let us derive each of the term. Del L over del phi is equal to m square phi, and del L over del mu phi. So, how will you derive del L over del mu phi? This is in the Lagrangian, only the first term will contribute. So, as you can see, this term only depends on del mu phi, this term is independent of del mu phi. So, we will consider this term here only. So, this is equal to del of del mu phi times half, this acting on half del nu phi del mu phi. If you notice, I have used the symbol nu here instead of mu. That is because I have a free index mu here. I must say that I am using Einstein's summation convention. So, whenever a symbol, an index is repeated, its summed over the values it takes. So, for example, if I consider a mu, the index mu here runs from 0, 1, 2, 3. So, a mu is just equal to a0 plus a1 plus a2 plus a3 and hence a mu is also equal to a mu. This mu here in this expression is a dummy index. So, we can put any level we want for this term here. That is what I have done in this expression. Instead of mu, I have used nu here. So, this is now equal to, so this implies del L over del mu phi is just equal to half times twice del nu phi times del of del nu phi divided by del of del mu phi. Now, what is this quantity here? This is just delta mu nu. So, this is nothing but del nu phi delta mu nu. So, this is just del mu phi. So, what we saw here is that no. So, let me explain the symbols again. Eta mu nu is just equal to 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. And now, delta mu nu is the identity matrix. Instead of 1 minus 1, this is just 1, 0, 0, 0 and so on. All diagonal elements are 1 and all off diagonal elements are 0. Now, when you look at this, if mu is not equal to nu, this will just give you a 0. If mu is equal to nu, this is 1. So, however, eta mu nu as well as its inverse eta mu nu, which is numerically equal to the same thing, eta 0 0 is 1, whereas eta 1 1, eta 2 2 and eta 3 3 are minus 1s. However, here you can see if no matter whether mu and nu, whether mu is 0 or 1 or 2 or 3, it always gives you 1 if identity if nu is equal to mu, otherwise it gives you 0. Therefore, this quantity here is has to be equal to delta mu nu, not eta mu nu. We are not using something like this delta mu nu. We are using, and also the tensorial property here is such that it is actually a mixed tensor. If you look at the Lorentz transformation property of this quantity, this does not transform like a contravariant tensor of rank 2, it transforms like a mixed tensor of rank 2. So, therefore, the index structure has to match, and also the notation that we are using is such that this is equal to delta mu nu. All right. Thank you. This nu here is actually a contravariant index, not a covariant index. Yeah.
It will become del upper mu phi. Now it will become eta mu.
I see. Okay. Thank you. So, this this is actually equal to eta mu nu. So, this is del mu phi. You are right. Okay, so let us summarize what we have seen here. What we say is what we find is del L over del phi is equal to m square phi and minus m square phi. Thanks, Alvin. Minus m square phi and del L of del mu phi is equal to del mu phi. So, now we can substitute these in the equation of motion, and what we see is minus m square phi minus del mu phi is equal to 0, or in other words this is just del mu phi plus m square phi is equal to 0. What we find is the Klein-Gordon equation. So, this field here is actually a Klein-Gordon field. Now, what we will do is we will find the Hamiltonian density for this system, and we will see what we get. So we have already introduced the Hamiltonian density. H is equal to del pi of x del L over del 0 phi minus L of phi del mu phi. So, this is equal to pi of x, and we can see from this expression that del L over del 0 phi is again del 0 phi. So, we can use this expression here. No. So, this is simply del 0 pi qi dot del 0 phi minus L. So, pi of x is del L of del 0 phi. This quantity is again del 0 phi. So, we can substitute this for pi of x. Then what we get is Hamiltonian density H is equal to pi of x del 0 phi minus half del mu phi minus half m square phi square. This is equal to pi square of x minus half del 0 phi square plus half grade phi square plus half m square phi square. We can again substitute this for pi of x, and then what we get is that the Hamiltonian density h of x is equal to half phi of x square plus half grade phi square plus half as you can see, this very simple system actually satisfies all the criteria that we have specified in the beginning of this lecture, in the sense that the system is actually Lorentz invariant, the action is invariant under Lorentz transformation, the equations of motion are covariant under Lorentz transformation. It is local because the equation of motion only is a two derivative, it contains only two derivative term, that therefore it is a local field theory, and the energy density has a lower bound, all the terms here are positive definite. Okay. So, this satisfies all the criteria. So, what we will do in the subsequent lectures is that we will start quantizing this very simple system, and then we will study more and more complex field theories. Okay. So, with this we will close today's lecture. Tomorrow we will discuss some of the symmetries and conservation laws, and then we will actually start quantizing the field theory. Okay.